Yes. Yeah. So today's session will cover some of the questions from the entire syllabus, so you guys can have a slight revision, and I will also add some extra questions to the document which I'm going to upload, so that you can take it like a mock test sort of thing. Okay. So the first question we have is, and also try to do all the other weekly sessions because in the exams most of the questions would be uh, solving problems, not the conceptual directly mugged up kind of questions. So if you have practice, you would be able to answer better in the exam where you have limited time. Okay, so let's see first question. So it's given directly true plastic strain and true stress, and we're also given the constant in the exponential law. Okay, so now we are supposed to calculate what is the true strain if the true stress is changed. So can one of you tell me where to start? Yeah. So sigma t is k epsilon t power n. Yeah. So now actually because one case is given and then constant is given. So the proportional constant is given. So the only unknown is the exponent n, right? So if we can calculate true stress 500 MPa is equal to K 900 MPa into true plastic strain 0.3 power n, we don't know. Okay. So 500 by 900 is equal to 0.3 power n. So if you just take natural logarithm, ln of 500 by 900 is equal to n ln of 0.3. So this way you can calculate n. Okay. So now we know n and we know k also. So for the unknown case where stress is given, we can directly estimate. So 700 is equal to 900 epsilon t power n, n we know now. Okay. So this way you can easily estimate epsilon t. I'm not going to solve till the numericals today because we'll like to cover more questions. So is this clear? Yeah. Okay, so let's move on to the next question. So this numericals also in the exam you might have to have a calculator with you because there are actually numericals given by sir in your exams. Okay. Yeah. So the microstructure of an iron carbon alloy consists of a proeutectoid ferrite and perlite. Now the mass fraction of proeutectoid ferrite is given as 0.5. What should be the weight percentage of carbon in the alloy? So can anyone tell me what is proeutectoid ferrite? Or in this iron carbon diagram, which is the ejected point? Yes. So this is the ejected point. Yeah. So pro is basically means primary. Okay. So now if you are exactly at here and then suddenly and then cool, you will actually have pure mixture. What do you call ejected mixture? So basically, if you have, you will have 100% perlite, right? This point. Okay. Now, if you are to the left of this point, any point, and then you cool down. So there is already some alpha formed. Okay. So at this point, what you have is alpha plus gamma, and at this point you have alpha plus Fe3C, right? Now this alpha plus Fe3C, it doesn't exactly look like alpha and Fe3C. What it looks like is alpha plus alpha comma Fe3C ejected mixture. Okay, the microstructure will look like this. you have separate alpha and you have separate eutectoid mixture of alpha and Fe3C. Okay. So this alpha which is already existing is called the primary alpha or the pro-eutectoid alpha. Okay. Is this clear? So because when you go from above the ejected point to below the ejected point, only gamma gets converted to ejected mixture. Alpha stays like alpha only. So here you have some fraction of alpha and some fraction of gamma. Alpha stays like alpha only. Whatever gamma, that becomes the ejected mixture. Okay. Now they have given uh, pro-ejected ferrite and perlite. So ejected mixture is called perlite, right? So they have given the ratio of this and this total ejected mixture of alpha and cementite. So is 0.5. So this is half of the total. Okay, both are equally. So when will that happen? So at which point above, at which carbon percentage case, just above the ejected point, if you cool down, you will get equal fraction of primary alpha and perlite. Can you tell? So let's see. Yes, exactly. So here we have this point alpha 0.022 and here we have 0.76. So if you are exactly here and then you will get complete uh, you will get 100% perlite, right? Yeah. And if you are here just above here and then cool down, yeah. So okay, that line will actually be only alpha. So there won't be any. So here you will have 100% pro-eutectoid alpha, right? Now, so at which point we will get equal contribution of both pro-eutectoid alpha and 100% perlite? So exactly at half, midway. So if you are here or if you are anywhere in between these two, once you cool down, you will get some fraction of alpha, primary alpha or pro-eutectoid alpha plus fraction of perlite. Okay. Now, how can we, let's say this carbon is C, okay, the carbon concentration is C at that case. So we can get this F like, so we need to see just above the detected point how much ever is alpha. So for that we can directly do 0.76 lever rule minus C by 0.76 minus 0.022. So this would be the fraction of alpha just above the ejected point. So this would be the fraction of pro-ejected alpha in the final case also. Okay. Now it's given this as 0.5. Okay. So then 0.76 minus 0.022 by 2 is equal to 0.76 minus C. So 0.76 minus of 0.76 minus 0.022 by 2. So this is basically 0.76 minus 0.76 by 2. So 0.76 by 2 minus of minus. Okay. So it's just the average because it's 50-50. But if it is some fraction f, then you would get correspondingly. Okay. Suresh, is this clear? No? Yeah. Okay. So let's move on to the next question. So this way, here you have eutectoid point, but you could have any point like eutectic or anywhere. It's the same thing. Primary means the phase which is already existing. Okay, and the other phase is the one which actually transforms. Yeah. So this question is based on the number of vacancies and vacancy energy formation. If you remember, in the first starting weeks, we have this thing. So can you guys tell me what should be the vacancies formula? So simple. This is the formula. Yeah. K is the Boltzmann constant. E is the temperature. EA is the activation energy to form a vacancy, and exponential. And this is the total number of vacancies, and this is the total number of atoms. So this follows an exponential equation. So this kind of equations are there wherever an activation energy is needed actually. Okay. So now here what we know is we only know vacancies per meter cube. So vacancies per unit volume is given, temperature is given, and vacancy formation energy we need to estimate given atomic weight or atomic weight, density, Avogadro's number, and Boltzmann constant. Okay. So because we know NV, but we don't know the N, right? What are the total number of atoms per meter cube? That's not given. So first we need to estimate that. So can any of you tell me how can we estimate the number of atoms? We know the density, we know the molecular weight. Number of atoms per meter cube. Yes. Yeah. Into Avogadro's number, right? Because we want number of atoms. Yes. So if you see density is grams per cc, right? And Avogadro number is atoms per mole. And atomic weight is gram per mole. So here if you see gram gets cancelled, mole gets cancelled. So you are left with atoms per volume. So this way you can actually confirm whether you have written the correct formula or not also, just doing the dimension analysis. Okay. So let's plug in the values. Density is 8.4 grams per cc. So centimeter cube, because we want in meter cube, we need to convert that. So 10 power minus 2 meter cube. Okay. Into Avogadro's number. 6 point, yes. Your voice is breaking. Ajay, your voice again, bro. Sorry. Maybe. No. I didn't say that. See here what I said. What we know is atomic weight is in terms of grams per mole. Okay. So we have above grams per cc. Na is atoms per mole. By we have atomic weight grams per mole. Okay. Now this I am writing as, yeah, atoms per mole into mole by gram. So now you will get atoms per cc. Okay. So because we want in meter cube, we are converting them. So in questions like this, if you actually put the units also, you might make less number of numerical errors. So that's a good habit to have. Okay. Now this is atoms per mole, and atomic weight is given as 63.5 grams per mole. Okay. So this way 8.4 into, so yes, I Yeah, I'm not able to hear you. Yes, yes, yeah, yeah, you can type it out in the chat. So this would give us the number of atoms in 1 meter cube. Okay, so this would be actually 7.9661 into 10 power 28 atoms per mole. Yeah, atomic weight is given as grams per mole. Okay, so if let's say 863.5 grams per mole means 1 mole of that copper would actually weigh 63.5 grams. Okay, yeah, yes. So yeah, now we know the n. So total number of atoms in 1 meter cube. Okay, now so we know the NV vacancies per meter cube. So NV by N is 3 into 10 power 23 by 7.9661 into 10 power 28. Okay, this is the ratio of vacancies to the total number of atoms. So this would turn out to be around 3.766 into 10 power minus 6. Now this is equal to, in terms of activation energy, this way you can write Boltzmann constant into temperature. Okay, so now if you take the ln, so this let's see, yeah, 12.4895 minus, so I am just taking ln. Okay, now EA is equal to KT into 12.4895. Now K, it's given in electron volt per atom Kelvin. So you need to carefully choose K, because we were asked this activation energy in electron volt per atom. So you can either specify in electron volt per atom or in joule per kg Kelvin. So based on that, you need to choose the units of K accordingly. Okay. Into temperature, we were given 500 Kelvin. So 500 into 12.4895 Kelvin. So Kelvin Kelvin gets cancelled. So you are left with electron volt per atom. Okay. So this is the activation energy. So is this clear? Yeah. 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 Yes. Yeah, yeah. Just substituting the K and the T. That's it. So whenever you are substituting, try to put the units also. Then it will be easier to handle. Okay. Yeah. So in K, you should be very careful, because based on what units you are asked the activation energy, corresponding units you need to take for K. Because Boltzmann constant, you have different. If you change the units, the values will be different. So, okay, I should be clear on that. Okay. So next question, we are asked a linear elastic material and elastic modulus is given, yield strength is given. What is the resilience? So we are given linear elastic material. So straight line, and yield strength is given. So what is the yield strength point actually? So when it starts plastic deformation, right? And we are actually given linear elastic part. So the entire thing would be linear elastic, and the point where it starts plastic is the yield strength. So this is sigma y, and elastic modulus is given. So the slope is given. What is resilience? Yes. So area under the curve in the elastic limit is the resilience. So how can I get this resilience? Area under the curve half into sigma y into epsilon y, right? Because it's a triangle, half into base into height. That's it. Now, because this is elastic, you can write strain as stress by elastic modulus. Okay. So it's just equal to sigma y square by 2e. So if you substitute the values, you will get the resilience. That's it. Okay. So only for resilience in the elastic regime we can do these simple calculations. But if you take the actual stress strain curve, and if you want toughness and all, you need to do numerical integration only. Okay. Yeah. So next again we have question in the phase diagrams only. So let's see this question. We have 50 weight% PB and mg is quenched to room temperature from high temperature so that the microstructure at high temperature is preserved. Okay. So we are suddenly cooling from some temperature and making sure that whatever microstructure is there at that temperature, that will stay at room temperature also. Okay. Now, the resulting microstructure has 63 is to 37 in ratio alpha phase and Mg to Pb. So if you see the phase diagram, Mg to Pb is one of the phases like cementite in Fe3C. Okay. Intermetallic compound. Now, what is the temperature from which we quenched? Okay. So we have 63 is to 37% of alpha to Mg to Pb. That means, so this is alpha, this is Mg to Pb, and this is alpha. So we are somewhere such that 63 is to 37 is the ratio. Okay. So this is the point actually at which a liquid starts becoming Mg to Pb and alpha. This is the liquid converting to both alpha plus Mg to Pb. So this is the eutectic point, right? Is it? Yeah. So here we have liquid converting to two solids. So it's a eutectic point. Okay. And here, yeah. So now we are not asking. They didn't ask anything about pro-eutectic or anything. They are just saying alpha is to Mg to Pb is in certain ratio. So let's say if you are here at this temperature, we want to know the temperature at which you will get that ratio. Okay. And then given this PBMG has 50%. So this line. So in this line, we are at some temperature. Because of that, we got 63 to 37 ratio. Okay. So let's say if you are at 400. So at 400. So this question, the only way we can do is because we don't know the exact equations, trial and error only. Okay. At 400 degrees Celsius, if that was the point, then no. We need to estimate the temperature at which the ratio to alpha is to Mg to Pb is given ratio. So, there is no basis actually. I am just trying. Yeah. Yes. So okay. First, let's start at 300. Okay, so if this is this point A, trial A, okay, now this what will be the alpha fraction? So this is let's take it as 81. Okay, and what would be this? Let's take it around 17. Okay, now the fraction of alpha at A would be, so this is 50 given in the question. So 81 minus 50 by 81 minus 17, right? So what would be this fraction? So 81 minus 50 by 81 minus 17. So 48.44%. So this is not the point we want. Now, can you tell me if we go up or if we go, yes? Yeah. We are actually given C. C is given as 50-50 already. Or I didn't exactly understand your question. We are already given the PB is to Mg concentration, and we were given the alpha is to Mg to PB ratio, mass fraction ratio, and then we are supposed to find out the temperature at which you can get this certain ratio. So what I am trying is, I chose some temperature 300. At that, if I do the fraction of alpha, I am getting only 48%. Now, can you tell me which direction should I go? What should be my next trial? Above or below 300? Yes, because if we go below, we are moving away from alpha, so the alpha phase will actually decrease if you go down. So we should move up. Okay. So the next trial I am trying at B. Okay. So this is 30. Let's take it as 32. So again same trial B at 400 degrees Celsius, fraction of alpha 81 minus 50 by 81 minus 32, right? So what would be this number? Oh, yes. So that I am not understanding. So okay, you will put x here. Okay, 81 minus 50 by, yeah, 81 minus x is equal to 63. So this is what you are saying, right? No. So yeah, alpha phase is 63. So let's assume at some temperature. So this point, let it be x. Okay. So what is saying is, at x concentration. No. At some temperature T, where alpha phase is that x, that point which it touches is x. Now fraction of alpha would be 81 minus 50 by 81 minus x. So that is given as 0.63. So now 81 minus 50 by 0.63 is equal to 81 minus x. So x is equal to 81 minus. So is this what you are saying? Yes. So yeah, I think, yeah, we can do this also. So this would give us x as 81.8. So now we can actually see the temperature at which x is 31.8. So that is around actually 400 only. Okay. Yeah. So yeah, as you said, this way if we do, we don't need to do the trial and error. We can actually get directly the answer. Thank you, Ajay. Yeah, it's given in the question. Yeah. So we usually give the temperature and then we have to calculate what is the fraction of alpha. But here the fraction of alpha is given, and we are supposed to estimate the temperature. Yeah. Okay. So again, next question. Uh, so which 50? 50 weight percent PB. Yeah? So this is that point, right? 50. The x-axis composition weight percent PB. Yes, 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 yes. Composition PB only. So the question is actually you are somewhere on this line. Okay, we don't know the temperature at which we are, but the composition is given as 50% of PB. So somewhere on this line, from there we are suddenly cooling, and we got 63 fraction of percent of alpha for an unknown temperature. Now the actual composition is on this, but at which temperature will it be 63% alpha? That is the question. Okay. Yeah. Yeah. So that 50 came here. So next question. True stress strain relation for a ductile material in the plastic deformation regime is given by. Okay. So they have given the relation between true stress and true strain. Now the exponents are also given. The unknown coefficients are also given. K as 500 MPa and N as 2.6. The true strain at the onset of necking. Okay. So can anyone tell me what would be this? In this case, no. Exponent. This K is the constant, proportional to constant. So at necking, for this curve, M is equal to epsilon T. What? Yeah. So, but we are given sigma T is equal to K into epsilon T power N minus 2, right? So, this for necking, uh, epsilon T would be N minus 2, right? So, because N is given as 2.6 minus 2, this is 0.6. So, this is the general case. But in this question, they have given a specific form, N minus 2. For some reason, they chose that kind of form. So, in that case, what is the true strain at necking they are asking? Okay. So, be careful. This is the true stress and true strain. These are not engineering stress and engineering strain. So, you need to, if they ask engineering stress and engineering strain, you need to convert them. Okay. So, in 1 week, we actually discussed that. So, you can refer back to that. Okay. Yeah. So, next question. Yeah. So, hypothetical FCC has a dislocation density 1 into 10 power 11 centimeter square inverse, and then shear modulus, and then lattice parameter, What is the stored energy density in the dislocations? So does anyone know the equations which we need to use here? The relation between stored energies in dislocations and the elastic energies and all? Okay, so I'll tell you. So actually the energy, total energy you can write in this case due to that dislocation happening as GB square by 2, where B is the magnitude of Burgess vector. Burgess vector. Okay. So here we are given FCC. So what would be this Burgess vector in terms of lattice parameter? Anyone? So Burgess vector is basically half of the unit cell lattice parameter into directions like in FCC that direction would be 110, in BCC it would be 111. Okay, so this is Burgess vector. So B is the magnitude of that, so that would be actually a by 2 into magnitude of 110 would be root 2, right? So G into a by 2 root 2 whole square by 2. This is the total energy. Now the dislocation density is the ratio of energy of stored in dislocations to the total energy. Okay. Now the dislocation density is given to us. We need to only estimate the energy stored in the dislocations. So okay. So it's given as 1 into 10 power 11 centimeters minus square. So centimeter is 10 power minus 2 meter minus square, and then E. So G is shear modulus 50 GPa. So 50 into 10 power 9 into A by root 2. A is given as 0.5 nanometers by 2 into root 2 whole square by 2. Okay. This would give you the energy stored in the dislocations or the stored energy density in the dislocations. Okay. Is this clear? So these are direct formulas I am using, and this is how you can actually like calculate the stored energy density and the dislocation density, the relation between these. Okay. Yeah, but this was one of the mock papers Sir has given me, so not everything. Some I created and some from the mock papers Sir has given. Okay. So the next question, length of the Burgess vector in hypothetical BCC. So as I said earlier, yes, 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 yes. Yeah, yeah. Sir is actually following the one which I told. I discussed with Sir and we were following that. And what she followed, I also found that formula, but we are following the book by Callister. So in that book, yes, 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 they don't match. Yes. So that problem only I faced. So we are following the textbook, Callister's. Yes, yeah, yeah. So can you remind me that question? I'll check again in the 1 second. Yeah, percentage of covalent to ionic bond. Yes, yes, yes. Yes, yes, yes. Yeah. Mm, I have the textbook in front of me, so I'm just checking the final formula here. Mm, yes, yes, yes. I understand. I understand. Follow the exponential formula which I gave. Okay. Yes, yes. Follow the exponential formula only. Exponential of minus 0.25 x minus xp whole square. Yeah, use that one. So yeah, here, uh, so the Burgers vector in FCC is a by 2 110, in BCC a by 2 111. Okay, so now we can estimate the because lattice parameter is given. That means basically A is given. We can estimate the length of the Burgers vector, right? So if it's FCC 1 by 2 into root 2, and it's BCC 1 by 2 into root 3. Okay. Okay, so let's move on to the next question. Yeah. So you might remember this question, a lengthy question we solved in our one of the weeks. So take your time to read the question. We will solve it again once. And I think this is the last question for today. I'll add some more questions and then upload the document tonight so that you can prepare well for your exam. Yes, yes, yes. So this, yes, yes, lengthy questions will have more marks. Where you need to do more calculations will have more marks. So this question can be given in two forms actually, because here only initial crack was given, and we are asked to estimate the total number of cycles, right? So you could actually this could be given in two parts where you need to actually estimate the critical crack length as part one of the question, and part two could be this total number of cycles. Because it's a lengthy question, it could be divided into two parts and given. So that kind of questions also you can expect. So that's why even if it is lengthy, actually try to do the assignment questions and whatever I discussed in the tutorials again. So practice you actually need in the short time to do. So just read this question once, and then I expect one of you to explain me from where to start, and then we'll do. Okay. Yes, yes, we'll solve this one. So first, what is happening is, can anyone explain what exactly is happening in this question? Yes, yes. So that is the second part. Yes, that is the second part. So what is happening is you have a large sheet you have an initial crack, and with the time, because of the loading, fatigue kind of loading, that crack length is increasing. And when that crack length reaches a critical level, then it fails. Okay. So this Paris law tells you, like, relates this rate of change of the crack with the number of cycles. Okay, with delta sigma or delta k. So we'll see that first we need to calculate what is the critical crack length AC. Okay, so this is AI and this is AC, and the Paris law relates actually. So how much this crack is growing with the cycles. Okay, and this delta k is basically beta delta sigma. So we know that stress intensity factor k is beta sigma root pi a, right? Yeah. So delta k is basically when you have this changing stress, delta sigma. That's it. So this relates these two. But so if you see here, dA you can write now as a power m by 2, and then c beta delta sigma root pi power m, okay, into dn. So I brought a to this side and everything else to the other side. So we can actually integrate this, and we can get the total n you need for the crack to reach its critical. But we don't know that intervals. So if you try to integrate here, AI to AC, we don't know this critical cracking. So first we will estimate that critical cracking. Okay. So to get that critical crack length, beta sigma root pi a. Okay. Now at critical crack length, when will that critical crack will happen? When the alternating stress is at its maximum value, right? So we have an alternating stress. So when do you think we are very close to reaching that, whether we are at lower stress or higher stress? Obviously at higher stress. Okay. Okay. Now they have given the nominal stress varies from 100 MPa to 1/2 of the yield strength. And what is that yield strength? 500 MPa. So sigma is actually varying from 100 MPa to 250 MPa. So in that case, and the Kc is given 25. So 25 MPa root m, yeah, is equal to beta. Beta is the geometric factor, so it is given here as how much did they, or they didn't give, m equal to 4, 1 of the, and h crack. Okay, so if nothing is given, just take 1. Okay, and sigma max 240 MPa into root pi a, right? So MPa gets cancelled. So no. See, nominal stress varies from 100 MPa to 1/2 of the yield strength. So stress is varying from 100 to 1/2 of the yield strength is 250 MPa. No, it's not the yield strength, it's the maximum stress in the loading. Okay, that's it. So if you do whole square, then this is pi AC. So this is in meters. So 0.01 by pi meters is the critical crack. Okay. So whatever this value comes out to be, so 3.2. Yes, exactly. Yes. now. So now we got the critical crack length. So we know the initial crack length given as 0.6 mm, and we know the critical crack length 3.2 mm. So if the crack length reaches this, it's failed. So in between, how many cycles we need? So that is the question. So yeah, let's do this. So integral ai, so 0.6 mm to 3.2 mm. So so when we are substituting here m c beta, we are taking 1. So this delta sigma is the variation between maximum to minimum. Okay. So sigma max minus sigma min, and a root pi power m. M is given as, c is given 5 into 10 power minus 11, and m is given as 4. So let's just take those values. dA by a square is equal to integral so this entire thing is a constant, right? None of them are functions of dn. So I'm just writing it this way. So c is 5 into 10 power minus 11 per cycle NPA power 4 and then B we are taking 1, and delta sigma as 250 to 100, so 150 MPa, and then root pi whole power m, which is 4. Okay. So integral dn is basically n cycles into 5 into 10 power minus 11. So per cycle, so that gets taken care of. MPa power 4, MPa power 4 gets taken care of. So yeah, so we'll have only 1 by m remaining here. So pi, root pi whole power 4, so pi square. So here a power minus 2 integral, so a power minus 1 by minus 1, 0.6 to 3.2 m. Okay. So this actually you can write it as 1 by AC minus 1 by I. Minus will be there. So this actually is 1 by AI minus 1 by AC is n into this entire thing. Yeah. So this entire thing is inside exponent power m. Delta k power m, right? Delta k is beta delta sigma root pi a whole power m. So delta sigma power m will come. Okay. So 1 by AI 0.6 mm, so 0.6 into 10 power minus 3, so 10 power 3 minus 3.2 into 10 power 3 is equal to this entire. So this way you will get the number of cycles you need. Okay. Yeah. So this is actually one of the most lengthiest questions in this topic. So that's why I wanted to cover it again once, and little tricky also. And that one misses stress, maximum shear stress, those and all, I think you might already know. I'm not going to cover that for the failure theories. But I'll give some questions and I'll upload this with some addition of questions. Okay. That I'll mostly do tomorrow or day after. For now, I'll upload this only. Yes, yes, yes. I'll upload with solutions also. Tomorrow or day after, I'll upload some extra set of questions. Okay. I'll upload this PDF and in the YouTube, I'll put the video, but the video of today only, not the new problems also. New problems only the solutions I'll put, questions and solutions, no video.